Hello ladies and gentlemen, welcome to section 6.7, fitting exponential models to data. What we're going to talk about here today is very similar to what we talked about with everything we've been doing in this chapter. We're also going to tie in some things that we talked about earlier in the year as far as getting data to match up with linear equations that we're going to write. So we have two different types of exponential equations that we've talked about. Exponential growth, that's also like a percent increase. Exponential decay, that's like a percent decrease. And how we're going to go through this, everything we've dealt with so far has always gone up or down by a constant ratio or a constant multiplier. We're going to notice now with the data that everything real world wise is always constant. So the first thing we got to do is find the average ratios between all the data points. So we have to find each ratio between each data point and then average that all up. Then we can then create our equation from there. But most of the work will be done with the data points right away, and then we'll be able to finish, hopefully finish the problem easily on the back end. Okay, so here's what we've got. We've got this table here. We're going to get this. So we have this table set up here on our screen, and so what we have to do is we have to find the ratios that multiply each one, so forth this way. Okay, so we're going to take 277 and divide it by 262. We usually try to go quite a few decimal places out for better accuracy, as we've talked about in class before. So 1.0573 is the first one. We have 1.0614 and then 1.0578, 1.0611, 1.0576, 1.0602, 1.0592, 595, sorry. That's a 5. All right. 1.0587, 1.0602, 1.0591, 1.0600, and 1.0587. Okay, so these are all the ratios, and how we find this is we take the second number divided by the first. Usually in tables like this, if you want to start at the bottom, go 523 divided by 594 and work your way up that way. That may help you out a little bit better there. So that's what we do here. Now to find that, what we're going to do is we're going to add all these numbers up and then divide by 12 because we have, or 13 because we have 13 different numbers here, or 12 different numbers I should say. We have 12 different ratios that we've got, and what that's going to give us is our average ratio is equal to 1.0593. Alright, so this is our average ratio between the numbers for each one. So now what we have to do is we have to write out our equation. And so our equation is y equals a, parenthesis, because these values are going up, we're going to use 1 plus our ratio, or 1 plus our ratio there, and that's going to be raised to the x power. So now this value here in the center is what we're going to put right there. Okay, so how this is going to work is our a value is our start at value. So I'm going to have y is equal to 262, and then we're going to have in my parentheses 1.0593. That's raised to the x power. Okay, this would be an acceptable answer for what we've got. Now they give us this 1 plus and 1 minus. How we can write that as well is y equals 262. We go 1 plus 0.0593, that's raised to the x power. Okay, so we can break up the 1.0593 into 1 plus. This would basically be saying it's going up by 5.93% each time. If we remember back to our percent increase and percent decrease problems there. So, that's what we have. If we were looking at a problem, and this is going off the book here, if our average ratio was going down or the numbers were going down, so our value was 0.75, let's say it started at 100, so we have y is equal to 100, parenthesis 0.75 raised to the x power, or 101 minus 0.25 raised to the x power. Okay, and why this and this are equal and why they look different, this answer gives us this. Okay, the 1 minus 0.25 gives us 0.75. You can write them either way and still get them credit as long as they equal what they need to be for the average ratio. Okay, so that's just a little heads up there. Most of you, I'm assuming, will just use this first example, but if you want to challenge yourself, you can definitely use the second example. Okay, so that's where we're at with fitting exponential models to data. If you have any more questions, make sure you let me know, and have a good day.